Yo, what's going on everybody? In this video, I'm going to teach you everything you need to know to start working with NumPy. So sit back, relax, and enjoy the show. NumPy, it's short for numerical Python. It's a Python library used for numerical computing. It's widely used in fields that involve heavy data processing such as data science, engineering, artificial intelligence, and machine learning. Python is currently the most popular language for AI and machine learning for a few good reasons. It's easy to read and write with, it has a massive ecosystem of libraries, and it integrates well with technologies like APIs, databases, and web applications. This makes Python a top choice for building and deploying real-world AI solutions. However, Python is really slow. That's where NumPy comes in. Under the hood, it's written in C, which is magnitudes faster than regular Python code. With AI and machine learning, you're often working with massive datasets and you need to do a lot of number crunching. Plain Python lists, not gonna cut it. NumPy gives us access to NumPy arrays, which are faster than native Python lists. Plus, with NumPy arrays, we can perform vectorized operations. For example, multiply all the elements by 2. With a Python list, multiplying a list by 2 would repeat all the elements twice. NumPy gives you the speed and the specialized tools you need to handle large-scale numerical operations efficiently. So, let's jump right in. Alright, let's get started everybody. You'll need an IDE to work with. Currently I'm using PyCharm, but the IDE you use is up to you. We'll need to download NumPy. It's an external library. We can do that by opening up a command prompt or a terminal. If you're using PyCharm like me, you can go to this terminal button in your toolbar. Or if you're on Windows, you can hold Alt and F12. For some reason, if those options don't work, you can always do a search for terminal. Terminal. Those are a few different ways to get to your terminal. We're going to type the command pip's our package manager, install NumPy. Enter. And then we just have to give it a little bit of time. Alright, we can close out of this window. After downloading NumPy, we'll have to import it. We do need to import NumPy into our Python file. You can type the following command. Import NumPy. Then for convenience, we can give NumPy a nickname or alias. Import NumPy as NP for short. Now to check the current version, you can type the following. You can print NP, that's our nickname for NumPy, dot dunder, meaning double underscore, version, then dunder again. This will print the current version, just to make sure that it's working fine. Currently my version of NumPy is 2.3.1. Moving on. Normally in Python, to create a sequence of data, you can use a list, you can use a tuple, you can use a set. Let's say that we would like to create a list of numbers. We'll name this list my_list. It will equal some numbers, 1, 2, 3, 4. Then we can print our list. Print my list, and we have the numbers 1 through 4. Let's say that I would like to multiply all of the elements by 2. With the native Python list, if I was to multiply this list by 2, let's say my_list equals my list times 2. This would duplicate all of the elements by 2. 1, 2, 3, 4, 1, 2, 3, 4. A NumPy array is superior to a Python list. It's faster and gives us more operations. Rather than using a Python list, here's how to create a NumPy array. Let's name this array just array. Equals access the NumPy library. Remember we gave it a nickname of NP. NP dot call the array function. And then pass in a list. 1, 2, 3, 4. And then we should be able to print it. Print our array. 1, 2, 3, 4. Just to verify that it is a NumPy array, you can print the following. You don't need to, but here's how. Print the type of our array. Our array is a NumPy ND, meaning n-dimensional, array. Then if you would like to multiply all of the elements by 2, all you gotta do is take our array equals array times 2. and that's going to double the elements in your array. Alright everybody, and that is your first lesson using NumPy. Hey, in this video I'm going to show you how we can work with multi-dimensional arrays using NumPy. Here's how. To create a NumPy array, we could say something like array equals access the library of NumPy dot call the array function, and then we can pass in one of a few values. A zero-dimensional array, think of it like a single point. I could pass in some value, like a character. This is a zero-dimensional array. And to check that, there's actually an attribute. Let's print access our array, access the attribute of ndim, meaning number of dimensions. The number of dimensions of our array is 0. It's a zero-dimensional array. If we had a few values within a list, let's add a few characters here. I'll just pick the first few characters of the English alphabet. A, B, C. This is now a one-dimensional array, like a single row. Now the number of dimensions that we have is 1. Let's convert this to be a two-dimensional array. I'll enclose our list within another list. And I'll add a few more lists. We'll add a few more letters. D, E, F, and then I'll just do some copying and pasting because I'm lazy. G, H, I. If you were to arrange your lists like this, they would form a sort of two-dimensional matrix. This is a 2D array. Sometimes people refer to it as a matrix. There's rows and columns. If I was to print the number of dimensions, that would be 2. It's a two-dimensional array. Now we're going to go to an even higher dimension, 3 dimensions. We'll enclose our 2D list within another list. And just for readability, I'll put each two-dimensional list on a separate line. Now we'll create a 3D array. We'll take our 2D array, copy it. Do pay attention to the number of brackets. We're not copying the outer set of brackets. Comma separate each 2D list. And then I'll replace some of the letters. I'll fast forward the video. Feel free to pause it if you need more time. Now, this is very important. I ran out of letters in the English alphabet. Each of these lists, they need a consistent number of elements with each other. It has 2 elements. All the others have 3. If I was to run this program, here's what happens. Value error, setting an array element with a sequence. The requested array has an inhomogeneous shape after 2 dimensions. We need a consistent number of elements within each list. This list has 2. All the others have 3. What you could do is add some sort of placeholder. I'll just use a space, but an underscore is another good option. Now this should run fine. Now the number of dimensions for our array is 3. It's a 3-dimensional array. You could go beyond 3 dimensions too. You can go to 4 dimensions, 5 dimensions, but that's going to be outside of the scope of the series. We'll stop at 3 dimensions to try and keep it simple. We have a 3-dimensional array. You can also access the shape using this attribute, the shape attribute. This will return a tuple of integers. It shows you the depth, the number of rows, and the number of columns. We have 3 layers. Think of it like it's a cake, a layered cake. That's the topmost layer, the middle layer, and the bottom layer. Each layer has 3 rows. 1, 2, 3. Each row has 3 columns. 1, 2, 3. If I was to remove one of these layers, the shape of our array is going to change. I'll delete the last layer. The shape of the array, it's still 3-dimensional, but it has 2 layers, 3 rows, 3 columns. If you ever need the shape of an array, you can access the shape attribute. Let's undo the last changes we made. Previously with the Python list, you would access an element like this. I'm going to print access our array, then you would use chain indexing. For example, I need the first layer that would have an index of 0, the first row, also 0, then the first element, the first column, also 0. That would print the character A. This is known as chain indexing. But with NumPy, we have access to something called multidimensional indexing. Here's what it looks like. You'll only be using a single set of straight brackets. Then comma separate each index. 0, 0, 0. That would print A. For the next element, that would be B. 0, 0, 1. 2 would be C. If I was to access 3, well, we would have an index error. Index 3 is out of bounds. For the next row, you would need row 1. Row 1, column 0. That gives you D. Row 1, column 1 is E. So let's see what 111 is. That is N. That's layer 0, because with programming, we tend to start with 0. This is layer 1, row 1, column 1. So that gives you N. That is multidimensional indexing, and it's actually faster than chain indexing. Here's an exercise. We're going to form a 3-letter word using string concatenation. We'll say word equals, now pick 3 letters. For me, I'll pick A, S, then S again. We'll access these letters via multidimensional indexing. For an A, I need layer 0, array, layer 0, row 0, column 0. And then let's print our word. Print word. That gives me A. Then I will add, using string concatenation, array at indices of, let's see, layer 0, layer 1, layer 2, layer 2, row 0, column 0. That would output AS. And then I'll add that again. Array, layer 2, row 0, column 0. And my 3-letter word that I picked is ass. So for your homework, why don't you use string concatenation and post a 3-letter word in the comment section? I might regret saying that. And that is an introduction to multidimensional arrays using NumPy. Yo, hey everybody, in this video I'm going to show you slicing using NumPy. Let's get into it. We'll need an array to work with. For this demonstration, we'll create a 2D array. Array equals np, call the array function, then we'll pass in a 2D list. There will be 4 rows and 4 columns. So within this list, we will have 4 nested lists. We'll have the numbers 1 through 16. That should be enough for this demonstration. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13, 14, 15, 16. Just for readability, I'll put each row on a new line. There we go, we have a matrix of data, a 2D array. For array slicing, we'll be using the subscript operator. I'll add this as a comment. We will access our array, use the subscript operator, which is a set of straight brackets. Here we will write a slice expression. There's 3 options. You can list a starting index, an ending index, and a step. Each is separated with a colon, a slice operator. Let's give it a try. Let's say I would like the first row in my 2D array. Here's how I would print that. Within a print statement, I'm going to access our array, use the subscript operator, which is a set of straight brackets. Then we will list where we would like to start. Let's access array at index 0. That's going to return the first row, 1, 2, 3, 4. Array at index 1 would be 5, 6, 7, 8. Remember that with programming, we tend to start collections with an index of 0. So that's why the second row has an index of 1. The second index would be row 3, 9, 10, 11, 12. Index 3 is 13, 14, 15, 16. Then if we access 4, it's out of bounds. You can also use negative indexing. Array at index of -1 would give you the last row, 13, 14, 15, 16. Or -2 would be the second to last row, 9, 10, 11, 12. That is the starting index. At which element would you like to start? You can also select a range. We need both a start and an ending index. Let's select the first 3. We'll start at index 0, colon, that's the slice operator, and end at 3. Now the ending index, it's exclusive. So if we need the first 3, that would be 0, 1, 2, 3. That will give you indices 0 through 2. Because the ending index is exclusive, we have row 0, 1, 2. Or perhaps I would like the first 3 rows after index 0, or row 0, so to say. Well, we'll start at 1 then, continue to 4. We'll skip index 0 and print the next 3 rows. If you would like to select everything up until the end, you can omit the second number, but you still need that colon. This tells Python select everything up until the end. Now we'll introduce a step. Let's select every second row, starting with the first. Row 0 and row 2. 0, colon, 4. This will select rows 0 through 3. Remember, the ending index is exclusive. Give me every second row. We'll add a colon, and then the step. We're counting by 2s. This will give me row 0 and row 2. 1, 2, 3, 4, 9, 10, 11, 12. If we're selecting all rows, you can omit the start and the end, but you still need those 2 colons. And the reason that you need them is because if we omit these, omit the colons, NumPy thinks we're selecting the second index. So with those 2 colons, if we omit the start and the end, we're telling NumPy select all rows. You can also set the step to be negative. This will return all the rows reversed. So we have the bottommost row, 13, 14, 15, 16, at the top, and the rows are in reverse order. I'm actually curious, what if you set this to -2? Oh, that's interesting. I didn't know that. Now the rows are in reverse order, and we're selecting every second row. I actually didn't know that. I was just curious. I was wondering what would happen if I put -2 here. Alright, so that is row selection. Now we'll get into column selection. Now we're going to get into column selection. We can select specific columns. This first column has an index of 0, because with programming, collections tend to have an index of 0 to begin with. This next column would have an index of 1. The third column has an index of 2, and the fourth column has an index of 3. When accessing our 2D array, we'll need 2 indices, for example, 0, 0. The first index is for the row, the second index is for the column. Now, if you would like to select all rows, for the row selection, we're just going to add a colon. Because without it, we're going to have a syntax error. Invalid syntax. For the row selection, we do need something here. We're selecting all rows, then access column 0. That would give me 1, 5, 9, 13. 1, 5, 9, 13. Column 1 would be 2, 6, 10, 14. Column 2 is 3, 7, 11, 15. Column 3 is 4, 8, 12, 16. If I set the index to be -1, that's going to return the last column, 4, 8, 12, 16. Or the second to last column would be -2. 3, 7, 11, 15. 3, 7, 11, 15. Now we'll select a range. I would like the first 3 columns. This would be column 0, column 1, column 2. We need a start and ending index. We'll start at column 0, so this number is going to be 3. because the ending index is exclusive. This will print the first three columns. We have 1, 5, 9, 13, 2, 6, 10, 14, 3, 7, 11, 15. That is the first three columns. Now we'll skip the first column, but print all the columns that come after. We'll start at column 1, or index of 1, so to say, continue to 4. So we skip the first column, this one, we're skipping it, and print all the columns that come after. If you would like all columns until the end of your data, you can omit the step, but you still need that colon. That works as well. Now we'll select every second column by setting the step. We'll be given column 0 and column 2. We have 1, 5, 9, 13, and 3, 7, 11, 15. Now I would like every second column, but we'll start at column 1. That would be 2. This gives us 2, 6, 10, 14, and 4, 8, 12, 16. Then you can reverse the order of the columns. Set the step to be -1. We have 4, 8, 12, 16, 3, 7, 11, 15, 2, 6, 10, 14, and 1, 5, 9, 13. If our step was -2, this would be in reverse order, but we're given every second column. 4, 8, 12, 16, 2, 6, 10, 14. Now we're going to combine both row and column selection. We'll need two indices. Let's say that we would like the first two rows, but only the first two columns. We'll start with our row selection. We're starting at row 0 and end at row 2. 0, 2. Then for the column, we need the first two. 0, 1, stop at 2. 0, 2. That's going to give me the first two columns of the first two rows. It's kind of like we're selecting a quadrant. This is a 4x4 matrix, and I would like to select these four numbers. Now we'll select this quadrant, 3, 4, 7, 8. Take a guess as to what you would have to write. We're selecting the first two rows. We can keep the selection the same for the rows, but for the columns, we're starting at, let's see, 0, 1, 2. 2, 4. But since we're selecting all columns till the end, we can omit the second number, but we still need the colon. So we get 3, 4, 7, 8. Now we'll select the last two rows, but the first two columns. What row are we going to start with? 0, 1, 2. Continue to 4, but since we're continuing to the end, we can omit the ending index. Now I would like the first two columns. That would be 0, 2. And that's going to give you this quadrant, 9, 10, 13, 14. Now we need the last two rows and the last two columns. We'll keep our row selection the same. Start at column, let's see, 0, 1, 2. Continue to 4. But since we're continuing to the end, we can omit the second number. And we should get 11, 12, 15, 16. This quadrant. Alright everybody, that is slicing in NumPy. I can't think of any homework for you to do, so to increase engagement for this video, why don't you post your favorite movie in the comment section down below. And well everybody, that is slicing using NumPy. Alright, let's do this everybody. So I gotta cover arithmetic and NumPy, cause well, it's kind of important. There's a couple different sections to this topic. We'll begin with scalar arithmetic. Scalar? It's a linear algebra term. Really, it just means a single value. We can apply operations with a scalar, a single value, to entire arrays. We covered a little bit of this in the first video in the series. We'll need an array to work with. I will create an array named array, np.array, then just add a few numbers. I'll add the numbers 1, 2, and 3. That's good enough. Then I will print our array. Now here's where scalar arithmetic comes in. we can apply a single value to each element within an array. If I were to take our array plus 1, each value would have 1 added to it. We have 2, 3, 4. Let's subtract 2. We'll just go through all the basic operations. Array minus 2, 1, 2, 3. Subtract 2 from each would be negative 1, 0, 1. Let's multiply by 3. Array times 3. Array times 3. We get 3, 6, 9. Array divided by 4. Array divided by 4. We get 0.25, 0.5, 0.75. Let's raise each element to the power of 5. The power of operator is 2 asterisks. Raise each element in our array to the power of 5. 1 to the power of 5 is still 1, 2 to the power of 5 is 32, 3 to the power of 5 is 243. That's basic scalar arithmetic. Scalar is a linear algebra term. It just means a single value. Now we'll cover vectorized math functions. A vector is another linear algebra term. A vector is a single dimension, such as a 1D list, whereas a scalar is a single value. Using vectorized math functions, we can apply a function to an entire array without writing a loop. Here's what that might look like. Let's say I would like the square root of each of these numbers within our array. Well, the NumPy library does have some built-in math functions, just like the math module. We'll access the library of NP, which is NumPy, call the square root function, pass in our array. The square root of each element are these values: 1, 1.4 and some change, and 1.7 and some change. We can round each value. Let's change these numbers: 1.01, 2.5, and 3.99. Let's round each number within this array. NP, call the round function, pass in our array. Here are all the numbers rounded. We have 1, 2, 4. To always round down, you can use floor. 1, 2, 3. To always round up, you can use ceil, meaning ceiling. 2, 3, 4. There's different built-in math functions you can apply to entire arrays. You can access them via the NumPy library. There's also built-in constants too, for example, pi, np.pi. That would return pi, 3.14159, blah 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 blah. Basically the first 10 plus digits of pi. Let's go over an exercise with vectorized math functions. Let's change our array to be 1, 2, 3. And let's say that our array is actually radiuses, or radii. I think that's plural for radiuses. I don't know, I'm a coding tutor, not an English teacher. We have an array of radii. Given each radius, we will convert it to be an area of a circle. We're going to combine both vectorized math functions and scalar arithmetic. So this is an exercise for us. Given our radii, we'll have to multiply them by pi. We can access pi via the NumPy library, np.pi, times, now the formula is pi times radius squared, times our array, which we have named radii, raised to the power of 2. And here we'll use scalar arithmetic. We're raising each element within our array to the power of 2. The formula to calculate the area of a circle, given the radius, is pi times radius squared. All of these radii converted to the area of a circle is 3.14, 12.5, and 28.2. So that was an exercise. For this next section, we have element-wise arithmetic. We'll have 2 arrays. Each operation is applied element by element between 2 arrays. We'll create array 1 equals np, call the array function. We'll pass in a list with the numbers 1, 2, 3 to keep it simple. Then we'll need a second array. We'll name this array array 2. And this array will have the values 4, 5, 6. With element-wise arithmetic, we can apply operations between single elements between 2 arrays. For this demonstration, I'll print array1 plus array2. This will add together the individual elements, one by one. 1 plus 4 is 5, 2 plus 5 is 7, 3 plus 6 is 9. Let's subtract array1 minus array2. That gives us -3, -3, -3. Let's multiply array1 times array2. We get 4, 10, 8. Let's divide array1 divided by array2. 0.25, 0.4, 0.5. Then let's raise array1 to the power of array2. 1 to the power of 4 is still 1, 2 to the power of 5 is 32, 3 to the power of 6 is 729. For this last section, we'll cover comparison operators. Using comparison operators, we can create Boolean arrays, filter data, and use element-wise comparisons. For this demonstration, we'll create an array of scores, like test scores. Scores equals NP, call the array function, then we'll pass in a list of scores. So these will be test scores. One student got a 91, another got a 55, one student got a 100, another got a 73, one student got an 82, and another got 64. Using comparison operators, let's see if any students got 100, a perfect score. What we're about to do will return a Boolean array. Print our array of scores that equal 100, a perfect score. We're seeing if any scores equal 100. This will return a Boolean array. It looks like there's one student that got a perfect score at element number 3, or index 2, 0, 1, 2. Let's see which students got a passing score that's equal to or above 60. This is the greater than or equal to operator. It looks like there's 5 students that passed. We have true, false, true, 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 true. Or let's see if there's any scores that are less than 60. Did any students fail? There's 1. We have 1 true. You also could use conditional assignment. For any scores that are less than passing, less than 60, we'll assign them to be 0. So if you fail, you don't get any points, so to say. We'll take our array of scores, use the subscript operator, then we'll take scores less than 60. We're selecting all elements within our array where the score is less than 60. Any that are less than 60, we'll assign them to be 0. And then we will print our array of scores. So now that one student would have a 0. They wouldn't get any credit if they fail. This all is a primer for filtering, which is another topic entirely, but it is a good time to introduce comparison operators. Alright everybody, that is different forms of arithmetic in NumPy. In the next topic, we'll discuss broadcasting. I couldn't think of any homework for you to do, so to help engagement with this video, comment down below where is your favorite place to take a vacation. And that is arithmetic using NumPy. Yo, hey everybody, in this video I'm going to explain what broadcasting is in NumPy. Broadcasting allows NumPy to perform operations on arrays with different shapes. Between 2 or more arrays, NumPy will virtually expand dimensions so that the smaller array matches the larger array in shape. There's a couple rules when it comes to broadcasting. 2 arrays are compatible. When matching each dimension, either the dimensions need the same size, or one of the dimensions has a size of 1. Let me give you a demonstration. We'll create 2 arrays. We'll have array1 equals np.array. This will be a 2D array. A 2D array with just a single row. I'll add the numbers 1, 2, 3, 4. That's good enough. Then we'll create a second 2D array. Array 2 equals mp.array. This will be a 2D array. This 2D array will have 4 rows, but 1 column. 1, 2, 3, 4. 1, 2, 3, 4. We'll print array1, access its shape attribute, and we'll do the same thing with array2. Print array2.shape. Taking a look at the shape of these arrays, can we broadcast them? Well, we have to follow those two rules. When matching the dimensions, they either need to be the same number, or one of them has a value of 1. We read these dimensions from right to left. These dimensions don't match, but one of them is a 1. These dimensions are compatible. With the next set of dimensions, these dimensions don't match, but one of them is a 1, so we can broadcast them. Let's test it. I'm going to print, I'll print array 1 times array 2. And there we go. We have a 2D array. Now the shape is a 4x4 now. We have 4 rows and 4 columns. We're virtually expanding the dimensions of our arrays. Let's say there's a mismatch between the dimensions. For example, for the number of rows for our first array, I'll change that to be 2. We'll add a second row. I'll add the numbers 5, 6, 7, 8, and let's see what happens. We get a value error. Operands could not be broadcast together with shapes 2, 4 and 4, 1. We could not broadcast these arrays together. We have a mismatch. The number of columns are broadcastable, either because these numbers match, which they don't, or one of them is a 1. These dimensions are okay. For the number of rows, these dimensions don't match, and neither of them is a 1. So we can't broadcast these two arrays. They're incompatible. They don't follow those two rules. If the number of rows were 4 for our first array, we could broadcast them then. We'll add a few more values. And one more row. These should not be compatible. We can broadcast them together. For each of these dimensions, they either match or one of them is a 1. For the number of columns, one of them is a 1. And for the rows, they both match. We can broadcast these two arrays together. Now for array 2, let's change the number of columns from 1 to 2. I'll just add in a few numbers. Now we can no longer broadcast these arrays. For the number of columns, they no longer match, and neither of them is a 1. But the number of rows still match. Those are compatible. So with broadcasting arrays, we can virtually expand their dimensions. Now for an exercise, we'll create a multiplication table via broadcasting. We'll say array1 equals mp.array. We'll create a 2-dimensional array, but it's going to have only one row, the numbers 1 through 10. Then for array 2, for our second array, this will be a 2D array, but it's going to have 10 rows and a single column. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we'll add the numbers 1 through 10. Let's see if they're compatible with broadcasting. I will print the shape of each array. Print array1.shape and array2.shape. Array2.shape. For the number of columns, they're compatible. They either match or one of them is a 1. For the number of rows, they are compatible. They either match or one of them is a 1. So we can broadcast them. Let's print array1 times array2. And we should get a multiplication table with the numbers between 1 through 10. The shape of this array that we have virtually created, it's a 10 by 10. 10 rows, 10 columns. So that's broadcasting. Broadcasting allows NumPy to perform operations on arrays with different shapes by virtually expanding their dimensions. I couldn't think of any homework for you to do, so why don't you comment down below what one of your favorite video games is. And well everybody, that is broadcasting in NumPy. Alright, let's do this. Aggregate functions. Aggregate functions summarize data and typically return a single value. In this demonstration, we'll go over a few simple aggregate functions, a few that you may need to know as a beginner. We'll need some data to work with. We'll begin by creating an array. Array equals MP, call the array function, and let's create a 2D array. I'll add the numbers 1 through 5, 1, 2, 3, 4, 5, and 6 through 10, 6, 7, 8, 9, 10. To sum all the elements in this array, you can use the sum aggregate function. I'll place this within a print statement. Access NumPy as NP, call the sum function, pass in our array. And we'll be given the sum of our array, 55. Or if you need the mean, there's a mean function. Print the mean of our array. What's the average? The average value, 5.5. If you need the standard deviation, that is STD. It's the measure of spread within your data. 2.8. This is more of a statistics term. But just remember, in the future, you do have access to a standard deviation function. Or if you need the variance, that is VAR. VAR. 8.25. The variance is the square of the standard deviation. Again, it's more of a statistics thing. You may not use it anytime soon, but you do have access to it. If you need the minimum value, there's a min function. np.min, pass in your array. This will give you the minimum value, 1. Or there's max. np.max, pass in your array. 10. If you need the position of the minimum value, there's a function for that. It's arg, meaning argument, min. What is the position of the minimum value? This function will return the index number, 0. That's the first index. Or the max, that would be arg max. Then pass in your array. What is the index of the greatest value? That is 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, with your set of data, you can select an axis. For example, I would like to sum all columns. Here's how I would do that. With a lot of these functions, you can select an axis for them too. So let's print np, call the sum function, pass in our array. Then with the sum function, we can pass in a second argument. I will select an axis of 0. If axis is 0, we're applying this function to all the columns. So here's our new array. We're summing all of the columns. We have 7, 9, 11, 13, 15. If I set axis to be 1, we're going to sum all the rows instead. And we should have 2 values within our array, 15 and 40. 15 is the first row summed. 40 is the second row summed. All right, everybody, those are aggregate functions. They summarize data and typically return a single value. There are more functions than what we've discussed, but those are a few of the beginner-friendly ones. And well, everybody, that is an introduction to aggregate functions in NumPy. Hey everybody, in this video I'm going to explain filtering in NumPy. Filtering refers to the process of selecting elements from an array that match a given condition. We're basically filtering out elements that don't match a condition. Here's an example. Let's pretend that we have 2 classes of students, 2 groups. I'll put them within a 2D array for this example. Let's name this array ages to store the ages of our students. Ages equals MP dot array, and this will be a 2D array in this example. We'll have 2 rows. Make up some ages. 21, 17, 19, 20, 16, 30, 18. Then we got one person that's 65 that's going back to school. So let's pretend that this is a college class. Some students are still in high school, but they're taking college classes, and others are older and they're returning to school. Now, for my second group of students, let's say one student is 39, that's Bob, 22, 15, one person's 99, 18, 19, 20, 21. That's good enough. By using filtering, we can filter out some of this data and create a new array. By taking our original set of data, we can filter out elements that don't match a certain condition, then use the elements that do match to create a new array. Let's say we'll create a new array of all the teenagers. Find anybody that's under 18. I'll create a new array. We'll name it teenagers equals, take our array, our original array, which we have named ages. Then here we'll write a condition. We'll create a new array where the elements match this condition. We'll say any ages that are less than 18. And then we can print it. Print our new array of teenagers. And it looks like we have three students under 18. 17, 16, 15. This is Boolean indexing. Now pay attention to the shape. By using Boolean indexing, this will flatten your 2D array. It's now one-dimensional. But there is a way to preserve the shape using the where function, but we'll get to that a little later in this video. This array of teenagers, it's a new array. By filtering out elements and creating a new array, we can preserve the original. We still have all the original students, the original ages of them. Alright, now let's filter out anybody that's between 18 and 65. We will say these are adults. Adults equals, take our original array, use the subscript operator, we'll write a condition. Return any ages that are greater than or equal to 18. Let's see what we have currently. We have a one-dimensional array, but we still have people that are 65 or older. We have 65 and 99. Here we'll need to use a logical operator. So let's enclose our first condition within a set of parentheses. Now with Python, to use the AND logical operator, you would write AND. But since NumPy uses C-style arrays, we have to use an ampersand. The ampersand is the C logical operator for AND. Now we'll match a second condition. Return any ages greater than or equal to 18, and any ages that are less than 65. Then let's take a look. We should have nobody that's under 18. We have two 18s, and nobody 65 or above. Doesn't look like there are any. Now you could use OR, which is a straight vertical bar, but we would have to change these conditions. So we'll say, if any ages are less than 18, or any ages are greater than or equal to 65, we would end up with an array of anybody below 18 or 65 or greater. So let's change that back. Those are logical operators. You can check more than one condition. We'll create a new array for seniors. Perhaps they get a senior discount. Seniors, take our original array, use the subscript operator, check all the elements within our array of ages. Is their age greater than or equal to 65? And we should have two. Let's print our new array of seniors. We have two students 65 or above. Someone is 65 and another is 99. Let's find any ages that are even. I'll name this array even, or evens. Take our array of ages, return any ages, use the modulus operator that gives you the remainder of any division. Modulus 2. If we divide one of these values by 2, if it's equal to 0, the remainder that is, put it within a new array of evens. Now we'll be given an array where all of the ages are even. 20, 16, 30, 18, 22, 18, 20. Or we can do odds. I'll name this new array odds. Ages modulus 2 does not equal 0. And then we'll print it, our new array of odds. We're now given an array where all of the elements are odd, not even. When filtering and creating a new array, if you need to preserve the original shape, there's a different function, the where function. Here's how it works. Let's create a new array of adults equals access NumPy, call the where function. We'll select anybody that's 18 or older, including seniors too. There's 3 arguments. The first is the condition. Return any elements within our array of ages that are greater than or equal to 18. Now the second argument is our array. And the third is a fill value. We want to preserve the original shape. If we're filtering out any elements that don't match the condition, we have some students that are under 18. We'll need to replace these values with something else. Let's put 0. Some people use -1. Some people also use NP, not a number, but we'll just stick with 0 to keep it simple. And then we will print our new array of adults. And it should retain the original shape. We have a 2D array, 2 rows, and let's see how many columns. 1, 2, 3, 4, 5, 6, 7, 8. It's a 2x8 shape. Any elements that don't match the condition are replaced with our fill value, which we set to be 0. But if I set this to be -1, well then, the fill value is -1. But we'll keep that as 0. The where function will keep the original shape of your array, but it's a lot slower than using Boolean indexing, which we have just discussed previously. I would only use the where clause if you need to preserve the original shape of your data, in this case, a 2x8. Otherwise, Boolean indexing will flatten your data when creating a new array. Alright everybody, that is filtering. It refers to the process of selecting elements from an array that match a given condition. I couldn't think of any homework for you to do, so why don't you post your favorite book to read in the comment section down below. And well everybody, that is filtering in NumPy. Alright, let's do this. Using NumPy, you may want to generate random numbers. It's useful for simulations, modeling, applying random transformations, and testing purposes. It's a good thing to know. Here's how you can use NumPy to generate random numbers. We'll need a random number generator. We'll give it a name of RNG, random number generator, equals, access the library of NumPy, which we've named NP, dot, random, dot, called the default underscore RNG method. We'll be using this object of RNG to generate random numbers. We'll start with integers because they're pretty simple. Within a print statement, I'll output the following. We will access RNG. There's a built-in method of integers. Then we'll pass in a range of values. Let's say you would like to roll a 6-sided dice. You need a random number between 1 through 6. The range will be 1, 7. The second number is exclusive, and you should get a random number between 1 through 6. I got a 2, 3, 2, 5. Now for readability, I like to use keyword arguments. I'll say low equals 1, high equals 7. It's not necessary, but I think this is more readable. Or if you need a random number between 1 through 100, I would set high to be 101, exclusive. So there I got a 68 and a 23. If you need a few random numbers, you can set a size. I need 3 random numbers between 1 through 100. Well, I'll set the size to be 3. I've got a 34, 82, 35. The random numbers will be stored within an array, a 1D array. If I need them stored in a 2D array, I'll set the dimensions. 3, 2. 3 rows, 2 columns. There we go. We have a 2-dimensional array of random numbers between 1 through 100. Now there's also something called a seed. If you don't set a seed, NumPy will create a seed for you. But if you need to reproduce the same results, you can set a seed. For example, I'll set seed to equal 1. And here are the results. The first number is 48, and the last number is 15. Remember that. If I were to run this program again, we get the same results. The first number is 48, the last number is 15. It's kind of like in Minecraft. If you use the same world seed as somebody else, you'll have another copy of the same world as your friend. Setting a seed is useful if you need to reproduce the same results. Now we'll cover floating point numbers. A floating point number is a number with a decimal portion, so to say. We'll be using a different method. I will print access NumPy, access random, call the uniform method. Uniform means uniform distribution. Each value has an equal chance of being selected. If I were to call the uniform method, here's what it would output. A random floating point number between 0 and 1. Now if you need a range, let's say -1 to 1, I'll set low to equal -1, high to equal 1. We'll get a range of floating point numbers then, between -1 and 1. Then you can also set the size. I need 3 random numbers. Size equals 3. We would store the random numbers in a 1D array. Or I could set this to be a 2D array, 3, 2, or some other size. Now we have 3 rows, 2 columns, and we are given random floating point numbers between -1 and 1. But you can change these values depending on the range you need. And to set the seed, you would use np.random, call the seed method, and then pass in a seed. Seed equals 1, or some other number. You would reproduce the same values if you use the same seed. Now we're going to learn how to shuffle an array. We'll create an array named array equals np.array. Pass in some numbers. I'll just say the numbers 1 through 5. 1, 2, 3, 4, 5. Then let's print this array. Print array. And we get the numbers 1 through 5. Now to shuffle this array, we'll need that random number generator again. RNG equals np.random.default_RNG. We'll use the RNG object, call the shuffle method, pass in our array. And this will shuffle our array. It should be in a random order. Here I got 5, 4, 1, 3, 2, 2, 3, 5, 4, 1. And that is how to shuffle an array. Now, if you need a random choice, we'll keep our RNG object. Let's say we have an array of fruits. Fruits equals np, call the array method, then we'll pass in a list of strings. Think of some fruit. I'll add an apple, orange, banana, coconut, one more, a pineapple. Let's output it. I will print my array of fruits. And it does appear to work. Now for a random choice, let's say fruit singular equals access the RNG object, call the choice method, pass in our array of fruits. We will print the fruit that we select randomly. A coconut, coconut, apple. Now we'll select more than one. I'll say fruits, then we'll set a size. I will pick 3 random fruits. I will set size to equal 3. Oops, and then we're printing fruits, not fruit. Here we go. I have 3 random selections. Apple, coconut, apple. Or if you need a 2D array, you'll set the dimensions. We'll have 3 rows, 3 columns. Apple, orange, pineapple, banana, orange, apple, coconut, pineapple, apple. This I discovered recently. For fun, let's change these to be emojis. Instead of the word apple, I'll add an emoji of an apple. Now we should output a 2D array, a 3x3 of fruit emojis. And they should all be chosen randomly. I've got a lot of pineapples here. Alright, so your homework is in the comments section to post a 2D array of emojis. If you can, pick some different emojis. Alright everybody, and that is how to work with random numbers, shuffling arrays, and random choices in NumPy.